this is Wala Saad. Let's continue discussing problems of assignment 2. In problem 13, we are continuing discussing the interpolation. Like you know or discussed before, that the interpolation is the function approximation. And this approximation can be applied with various techniques and methods like the Vandermonde Interpolation, the Lagrangian Interpolation, the Newton, and then the least squares and the orthogonal least squares. Of course, we might interpolate into any function, but we decided to discuss the polynomial interpolation for its benefits. There is huge benefits of using polynomials. Like if we need to evaluate the polynomial at a certain arbitrary x node value, we will use the Horner scheme in that case, right? Also, in deriving the derivatives, it's very easy to deal with derivatives of polynomials and direct, as well as in establishing procedures to find the unknown coefficients in node A1 and so on, and the polynomial approximations that we dealt with in Math 2, like the Taylor series. The only thing that we need to avoid is dealing with big amount of data or large number of points and close values. So if we have the absolute difference between two successive values is very small, this is a situation which we need to avoid. For our simplicity interest, we will be dealing with determining or finding the most basic polynomial for given set of data x naught y naught through xk yk. So if you are given only 1 point coordinates, we can interpolate it into a polynomial of degree 0, which is the horizontal straight line shown. If you are given 2 points, we can interpolate it into a polynomial of degree 1, which is a straight line. We are familiar with the straight line equation using the point form, and we can rewrite this form into the slope intercept form. So moving this y naught in the other side and taking the x naught distributed to that term, and we will then construct that term, which includes only x naught y naught and x1 y1, which is the free term, and the change in y by the change in x, which is the slope or the coefficient of the x. Of course, we might interpolate that given previously point into higher degree polynomials, and in that case we will not use the horizontal straight line or the constant polynomial. We will use the straight line of a higher degree. As you see, which line would interpolate, which line we would use. Here as well, in the 2 points interpolation, if we used higher degree polynomial, for example, instead of the straight line, we used the parabola. Which one we will use, this downwards or that upward one? So this case, we will suffer from more than one possible solution, and it's unclear how to distinguish between them. Dealing with that straight line of positive slope is different than dealing with that one with negative slope. And like we said here, this one is downwards and that one is upward parabola. Also, the behavior of every one is variant or different. So we have to stick to the property of the minimum necessary. For n plus 1 given points, we will interpolate it into polynomial of degree n. This polynomial is unique and it exists. So this is the property. The given data will be like we see here, either discrete data points, the points are read from or experimented in any laboratory, or an explicit function, and of course we will be given the function itself and its domain of interest in the interval form. So we can deduce as well a set of data and go in the interpolation techniques. So the Vandermonde interpolation, the idea basically is that we need, given set of data points, establish this polynomial or derive and commute this polynomial from a given data points. The Vandermonde did what? He established a polynomial for every pair. So for x naught, y naught, we can here substitute x by x naught, and this will be definitely equals to y naught. So we need to satisfy every point. We need this polynomial to output the corresponding y of every given x. And of course, this form is very famous. We have dealt before in Math 1 and Math 2, in Math 2 actually, and maybe Math 3, in solving linear system of equations in that form. So it's beneficial to transform it to the matrix form, such that this matrix, which we used to use it as the matrix of coefficients, and that vector is the vector of unknowns, and then the output or the external vector. Here, the coefficient matrix, we will think about what is given. The givens here is the x values, not the coefficients like before. So we will use the first column, fill it with x to the power of 0. Of course, it's basic for any x value. Raise it to the power of 0, it will give you 1. So we have column of 1s. And the second column is the x values itself. So here we will set the given x values, and then we have x to the power of 2 in column 2, and we will here we will use the square of the values in column 2, and so on till we drive or establish the Vandermonde matrix. This is the basic matrix for this technique. And we can solve this system using the Gaussian elimination, like we did before. Of course, this Gaussian elimination has main drawback, which is the number of operations required. Remember, solving the Gaussian elimination matrix, starting with the augmented matrix and then reducing using the elementary row operations, we were dealing with n+1 here by n+1 linear system of equations, which requires n to the power of 3 operations. So the operations is examined and is measured as of order n cubed, which is very expensive. If we discussed for evaluating the polynomial at any arbitrary value, it will be very easy because we are dealing, we might use the Horner scheme in that type. Also, the availability of the derivatives, it can be deduced, and it's simple and clear because we're dealing with polynomials. The second drawback is the incremental interpolation. So if we did all the steps and interpolated the n given points into n-1 polynomial, and we are given suddenly after this interpolation another data set, in that case we will need to repeat the whole steps from scratch in order to deduce the n+1 new polynomial of interpolation. In problem 3, we are required to find the Lagrange and Vandermonde for the given data set. So for the Vandermonde, like we discussed, we will establish the equations using the given set of points x0, y0, x1, y1, and x2, y2 for interpolating into quadratic polynomial. Let's here think what is the unknowns. We are given the x0, the x1, and the x2. So the unknowns are the coefficients a0, a1, a2. Let's establish, we know that these equations are derived, and we can substitute for the x value and its corresponding y for every polynomial, establishing the system. But you don't have to write it, of course. We just here discussing. You can directly write the augmented matrix form using the x to the power of 0 in the first column, the x's in the column 2, and the square of the x's in column 3 of the outputs or the y corresponding values. Directly write the augmented matrix and go in reducing it. Let's remember the elementary row operations. So here, in order to eliminate that 1 using the above 1, we will multiply row 1, yes, by -1, and then add it to row 2. And this will deduce this updated row 2. And then to eliminate that 1 by using the above 1 in row 1, we can do these 2 operations in one step, like you know. we will multiply again row 1 by -1, but that time added to row 3, and in that case we will have this row 3. Finally, in order to eliminate that one using the above -2, we might multiply row 2 by -½ because this will eliminate the 2, right? And then we will add it to row 3 and write here the solution like we see. Taking this reduced form of the augmented matrix, the last step is to back substitute. Yes, so from row 3 here we can read it as A2 is equal to 5 directly, and then A1 plus 2A2 is equal to 2, and finally A0 plus 2A1 plus 4A2 is equal to 11. Solving these equations together, we will successfully derive the coefficients, and we will substitute it in the polynomial of second degree that we addressed in the beginning, and here we go with the polynomial interpolation of the Vandermonde technique. We can do the same steps but with the Lagrangian interpolation method. For example, first let's discuss this 3 points, interpolating in them using the Lagrange functions. We have for 1 and its corresponding 2, and we are given 2 with the corresponding -3 and 4 with the corresponding 0.5. If we successfully established a polynomial for every point that filters the first one and assign 1 to it and then 0 to the other 2 values, here we will filter the second x value and give it 1 and the other values 0. The third polynomial we might successfully reach it, which gives us 1 and the 4 at x equal 4 and 0 elsewhere. The next step is to scale these 3 polynomials with the y values. So multiplying the first polynomial with 2 will get this 1 into the 2, right? And scaling this polynomial with -3, first it will be inverted because it will be -3, so it will look upwards, and then this 2 will be at downward at -3. And scaling the last polynomial into half, this will get the 4 reduced into half. Adding these 3 polynomials will construct this polynomial interpolation that we are addressing for the given data set. Why all this? This is from where the Lagrangian functions were given. So this Lagrangian function is equal to 1 for a given point and 0 elsewhere, right? For the given n+1 data points. We can interpolate these given data set into this polynomial after scaling these polynomials that we discussed, that filters a certain point and dismiss the other points. So this polynomial here should first filters the x0 and then scale it with the y0 and so on. So we will have a sum of, or the sigma of y sub I multiplied by L sub I L for the Lagrangian function. Of course, these polynomials are polynomials of degree n. We might rewrite them in the form of factors like this because they are of n roots. So we might rewrite it in n factors, the product of n factors like this, and scaled by a certain constant, which is here c sub I. This Lagrangian function should be equal to 1 when I is equal to j. So taking this case, when this function is equal to 1, at x equal x sub I. So we will here substitute the x by x sub I and substitute the L sub I by 1. So at 1, this x will be xi, right? So here we can deduce that this constant is 1 by that product. This product of factors can be rewritten using this capital Pi like we do with the summation and the sigma. So the Lagrangian function is the products in the numerator of the x minus all the given values except the ith. term, and in the denominator using this ith term and subtract from it all the other given values. We might rewrite these products as using the capital Pi, products of x minus xj, and here using the xi or the ith term for the corresponding Lagrange function. So this interpolation technique won't suffer from the n cubed order of operation, but instead of n squared, so we have n subtractions and n multiplications like you've seen, which deduce n squared operations rather than the n cubed of the Vandermonde, the previous method. So it's very easy and it's of less cost, but we are still facing the incremental interpolation. So if we successfully interpolated the given data into a polynomial and we are given another extra point, we will have to repeat the whole steps again. However, it's very easy and it overcame the n cubed order of operations, which of course decreased the accumulated error and the using of the space and so on. So let's back to problem 13. Here we need to interpolate using the Lagrange. We have 3 points, so we are establishing a polynomial of degree 2, and this is the form of the Lagrange interpolation polynomial. Y0, Y1, Y2 are given in the data. We need to commute L node, L1, and L2. Like we said, L node will use in the numerator all the points instead of X node, instead of its term, X value. So here, the L node derivation will use in the numerator x minus the other values of x, except x node, but in the denominator we will use x node instead. So here x node is prevented. Here we are repeating x node minus successively all the other values and given the product, and then we substitute. It's beneficial in that part to write over the table that this is the y naught, okay, and here write that this is the y1, and here write that this is the y2. Do this and again in the x values, x0, x1, x2, so that when you are here substituting these values, you will just look and not calculate or take care of the order in each time you are substituting. Reformulating or approximating this value, rewriting it to x squared minus 3x by negative 2, and then let's get the L1, L sub 1. Again, we use all the x values instead of only we will dismiss the x1. So we here subtract x minus x naught, which was the 2, x minus x2, and in the denominator we use this x1, the term of the Lagrange function that we are commuting, and subtract from it all the other values. Of course, you will notice if you didn't memorize the step, you will notice if you subtracted x1 minus x1, you will see that this is 0 and 0 is forbidden to divide with. So this step you will never forget. Now let's rewrite this form. We have here the x squared after substituting the x squared minus 5x, right, plus 6, and then over negative 2 times negative 3, which is 6. And then commute the L sub 2. Again, we use x minus x node and x minus x1, so we only missed the x2, and in the denominator we will use this x2 this time minus every other value of the given x values. And let's rewrite this given after the substitutions. We will have it x squared minus 2x, right, divided by 3 minus 2, which is 1 times 3, which is the 3. Now using the L sub 0, L sub 1, and L sub 2, the Lagrangian functions, and substituting in this interpolation polynomial of Lagrange, we will find that we have the 11, which is y0 multiplied by L0, plus the 7, which is y1 multiplied by L1, plus 28, which is y2 multiplied by L2. Rewrite this form, of course, to be more descent into the 5x squared minus 8x plus 7. That is the Lagrange interpolation second order polynomial versus the Vandermonde, which was here. This is 5x squared minus 8x plus 7. Okay. And here we have 5x squared minus 8x plus 7, the same polynomial. Because of the small number of data points here, we got the same points, and it's not quite clear the reduction of operations that happened using the Lagrange function. Thank you for your attention. Goodbye. Problem 14, construct a polynomial of order 4 using the Lagrange interpolation based on the table of data listed in problem 12. Let's recall the table of problem 12. Here is a huge number of points. If we need to interpolate it into polynomial of order 4, think about the minimum necessary property we discussed in the previous problem. So how many points do we need? For interpolating into a polynomial of order 4, yes, this is the n. So we need n plus 1 points. So how many points do we need? Exactly 5 points. Let's select any successive 5 points. I selected the first 5 points. And then what is required? The Lagrange interpolation. Remember the Lagrange interpolation polynomial? Yes, we will indicate it. So it's of fourth order. So it's y0 L0 plus y1 L1 plus y2 L2 plus y3 L3 plus y4 L4. What is the next step? Yes, it's to commute and drive the L node L1, L2, L3, and L4. Start with L node, where we will avoid using the X node at the numerator and then use it successively in the denominator. So the numerator of L node is the product of x minus all values except x node. X minus 0.6, x minus 0.8, x minus 1 times x minus 1.2. In the denominator, we will use this x node, the same term of L node, and then 0.4 minus 0.6. Of course, we will not use 0.4 minus 0.4. So 0.4 minus 0.6 times 0.4 minus 0.8 times 0.4 minus 1 times 0.4 minus 1.2. So here is the polynomial, and substituting in the points using x1, x2, x3, and x4, and then rearranging this by distribution of this constant, and then multiplying every two brackets, and then the product here multiplied by the third, and what's output multiplied by 4. Of course, these are algebraic steps that are trivial to all of us. Just be careful and be patient, of course, and then rewrite it in a decent form of polynomial with order 4. This is the first Lagrangian polynomial. Moving to L1, the same thing. We will avoid using x1, so we will multiply x minus x naught 0.4 times x minus 0.6 times x minus 0.8 times x minus 1 times x minus 1.2. In the denominator, we will use this time the 0.6. So the 0.6 is minus 0.4, and then 0.6 minus 0.8 times 0.6 minus 1 times 0.6 minus 1.2. Multiply the numerator and deduce the constant of the denominator, and here, after doing this algebraic rearrangement, we will get the last line. Again, for L2, we will use the x2 in the denominator and the x minus all other values in the numerator, multiply algebraically and deduce the polynomials. Finally, we will substitute these derived L node, L1, L2 through L4 and scale them with the corresponding y values of the x of its term, and then rewrite it in that form. In part 2 of this problem, it was required to use problem 12, from where we got the table, that huge table of big numbers. Part E, we were using the interpolation of Vandermonde for the same points. So if we evaluated the interpolation polynomial of Vandermonde at x equals 0.9 and this deduced polynomial of Lagrange again at x equals 0.9, we can find that the absolute difference or the absolute error that we call it, of course it's an accuracy measure, it's very small. Why do you think this error is very small? Of course, because we used small number of points, but if we increase the number of points, the error would become larger and larger. But of course, this is not a general interpretation for all types of functions because the number of points, of course, affect and also the position of the points from the beginning, from the middle, from the end of the table also varies the polynomial and reflects into the error. Okay, let's recall the Horner evaluating using Horner in evaluation. So we are ordering here all the coefficients 8.685 and the second, the third, and so on, all the coefficients in blue here in the first line, and then the 0.9, which is the value or the x node. We will multiply first, the first coefficient is dropped as it is because it's added to 0. Here we did plus 0, so it's dropped as it is. Okay, what about the second step? We will multiply this first coefficient by 0.9. Multiply, so we multiply these two numbers and equal, the equal stated here, this number will be written, and then we will add it to the third degree coefficient, this addition, and its equal is below here. And then again multiply this value with 0.9. The value will be written here, added to the above coefficient, and then write it down. Multiply again with 0.9 and so on. It's symbolically written here. So this is the B5, which is the same as the fifth coefficient of x power 5. And then we will multiply this B5 by the x node plus the A4 or the fourth, the x power 4 coefficient, and then here the x power 3 coefficient is added to x node, which is the term, the 0.9, the value, the arbitrary x value that we are dealing with the B4 or the value we got here, and so on till we find here the P sub 4 of the 0.9. So this is the evaluation of the fourth degree polynomial at x equals 0.9. And of course, this polynomial were deduced from the Lagrangian method. Thank you for your attention. Goodbye. Hello, everyone. Let's continue discussing classwork 2 problems. This is problem 15, the Newton interpolation. It's an alternative technique for the interpolation which allows an efficient evaluation as well as it allows incremental construction. Remember the drawback of Lagrange that we discussed? If you added a data point to your data set after finishing the interpolation or getting the interpolation polynomial, you will have to repeat the whole steps from scratch. This technique is allowing us to increment the construction of the interpolation polynomial like we will see. It also allows the both coefficients as well as derivatives evaluation, and it's based on the divide difference table. Like you see, the only operations done here is the divide and the difference. We set the x values in the first column, the y values in the second column, and in the third column the divide difference or the approximate of the derivatives using two successive points. So here, step 0, we are given the data points as usual, and we seek to interpolate them using the Newton interpolation technique. So we will set the x values in the first column, the second column the 0 degree polynomial which are directly the corresponding y values for every x, and in the other step we establish the polynomial of degree 1 which uses 2 points rather than 1, so as if this polynomial of degree 0 is directly using only x naught. So it's f of x naught. Here we use in the function the y naught and y1. This is the f of x naught and f of x1 as well as x naught and x1. So we are using 2 points. This is polynomial of degree 1, and in more in more discussed way. So the first column are the x values, the second column is the corresponding y's, the third column is polynomials of degree 1 using the divide and difference of the 2 points, and then using the other successive 2 points, and so on, going farther to the right side. So here, this is an illustrative example, simplified, so it's more illustrative. We have the x values and the corresponding y's. They are stated here in the first and second column. This is the polynomial of degree 0, and then increasing to the polynomial of degree 1, which uses 2 points, the y naught y1 and x naught x1, and then moving with a higher degree polynomial, which uses at that time the f of x naught x1 and f of x1 x2, as well as here x2 and x naught. So as if we're taking the first x value and the very last one, skipping the x1 in between, and so on, moving till farther till the right side. So after that, we get together these coefficients. We might gather them in the forward attitude or the forward behavior or the backward behavior according to the position of the points used in the interpolation among the full data set or the data that we have derived these data from. But we always use this forward construction. Now this graph illustrates the original function in blue and the Newton interpolation in orange. Like we see here that they both here coincide in the sampling points or the interpolation points at x equal -1, at x equals 0, at x equal 1, at x equal 2. Both functions satisfies these 4 points. The dashed curves here illustrates the polynomials in our way of constructing the interpolation. So in the orange is the polynomial of degree 0, the purple is the polynomial of degree 1, and so on. It's enhanced till it reached the orange curve. This curve, other graph here illustrates the original in blue, and in purple the Lagrange and the Newton both coincide, because you know the uniqueness theorem, the existence and uniqueness. So the both techniques gets the unique interpolation polynomial in the purple. They satisfy the same exact or original data at the interpolation points or the sampling points. So our problem, using this data set, we need to find the Newton interpolating polynomial for the function values in the given data and approximate the first and second order. Let's start by the Newton interpolation. Given the data points, how many points are these? 4 points. Yes, so we might build a polynomial of degree what? Degree 3. So we know if the points are of n plus 1, right? Then the polynomial is of degree n. This is why it will be n equals 3. So let's go to construct the divide difference table. Here we stated the x values, like in the table, the corresponding y values, which represents polynomial of 0 degree, and then construct the higher degree polynomials. So here this 2 comes from the -3 and then -1 over 1 minus 3, right? This is -4 over 1 minus 3, which is -2, and here is 2. Perfect. What about 5 over 4? Yes, this is 2 minus -3, so it's 2 plus 3 over what? Over 5 minus 1, which is 4. So it's directly 5 over 4. And that 2, it's 4 minus 2, and then over 6 minus 5, which is 1. So it's directly 2. And then again, we use the 5 over 4 along with the 2. So we use now the 5 over 4 minus 2 over what? Over 5 minus 3. Perfect. And this will get -3 over 8. And then we move to 2. It's 2 minus 5 over 4 and divided the 6 minus 1. And we construct the 3 over 20. Finally, the 7 over 40 comes from the 3 over 20 minus -3 over 8, and then take the last x value minus the first x value. And this is a checkpoint that we use the last and then minus the first. This means that we went correct in constructing the table. After constructing the table, we would pick up the coefficients like here. So we take the forward coefficients starting by y naught as b naught, and then 2, negative 3 over 8, 7 over 4. We will substitute b naught, b1, b2, and b3. And then the b naught is the 0-degree polynomial, so it's times x to the power of 0, which is 1. Here it has to be times x, right? So times x minus x naught. And here it should be times x squared, so it's times x minus x naught times x minus x1, which is driven from the Taylor expansion, like we discussed in the lecture. And then we can distribute and combine the like terms up till reaching this decent shape of the polynomial of the third degree. Now let's approximate the first and second order, as we see that it's direct polynomial, and we can get or evaluate the derivatives by dropping the power and then subtracting 1. So 3 times 7 is 21 by 40, and then x squared minus here 21 by 40 x squared minus times 2, the 2 will simplify with the 40, so it's 78 by 20x plus 301 over 40. And the second derivative is applying the same at the first derivative, dropping the power and subtracting 1, and here we go. Usually this problem might be extended to evaluating the derivatives at a certain point, and this is where we are going to use this polynomial and usually drive it using Horner for less accumulation error, like we know. So wrapping up the Newton interpolation, we construct the first column with the x values, the second column with the corresponding y values representing the polynomial of degree 0 in the interpolation, and then enhancing this interpolation into a polynomial of degree 1 using 2 points, and then using the 3 points, and so on. So here we're using the combination and up till reaching the last coefficient, and then we take these coefficients circled in red, orange, yellow, green, and blue, and then put them substituting in the polynomial interpolation of Newton. Let's continue discussing problems of assignment 2. Problem 17, use Newton's interpolation to represent the function f of x equals sine x on the interval x from 0 to pi over 4 into a polynomial of order 3. Remember that we have said before that the types of given data would be discrete data points or an explicit function, and in that case we need to identify the interval of the interested domain. And here we have from 0 to pi over 4, so we need to interpolate the function sine x from 0 to pi over 4 into a polynomial of order 3. Of course, all the methods that we have discussed, the Vandermonde, the Lagrange, and the Newton, use equidistant points, like we have noticed. So in order to deduce how many points do we need for a polynomial of order 3, for a polynomial of order n, we need n plus 1 points, so we need 4 points. How to establish the equidistant points from 0 to pi over 4? Actually, we will use the step length, so we need to commute or calculate the step length. Taking the interval from 0 up till pi over 4, we will subtract this step from pi over 4 to pi over 4 minus 0, and then we will divide it by the degree of the required polynomial, which is 3 here. Of course, this is the Newton polynomial that we will be able to construct after deducing the divide difference table. So our sequence of solving will start with the divide difference table, and then we will be able to substitute the b values here in this Newton interpolation polynomial. First, we need to derive the points that is required. So here the step length, denoted by h, will be b minus a. This interval here starts at a and ends at b, so we use pi over 4 minus 0 divided by the degree of the required polynomial, which is 3 here, and this of course gives us pi by 12. This is the step length, which means that starting by 0 we'll move to 0 plus pi over 12, and then pi over 12 plus pi over 12, and so on. constructing the x values, use the function in order to fill in the corresponding y values. So now you know how we constructed this table from this function among this interval of interest, right? And then we will construct the divide difference table. Again, you will write the x values in the first column and its corresponding y values in the second column. Moving constructing the f prime using the previous two y values, so the difference between y1 and y0, divide by x1 minus x0. This is 0.99, and here 0.92 is the 0.5 minus 0.26, divide by pi over 6 minus pi over 12, and here, for example, the negative 0.23 is the 0.8 minus 0.9, divided by pi over 4 minus what? Yes, we skipped, and we will go here with this pi up and then up to the pi over 12. Finally, we will, the last value is deduced from negative 0.23 minus negative 0.13, and then go down, down, down till you use the last x value minus here, go up, 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 and then horizontally the first x value, constructing the last b, which is b sub 3, substituting these b's values in the forward Newton divide difference table into the polynomial here, and substitute, of course, the x node, x1 and x2 values from the constructed table. You will get that sine x can be approximated in the third degree polynomial, of course, from 0 to pi over 4 by this polynomial deduced after, of course, distribution and combining of like terms. Thank you for your attention. Goodbye. Now we are wrapping up the Lagrange and the Newton interpolation techniques. This exercise using Lagrange and Newton's approximation to find polynomial that interpolates the given following data, comparing the result polynomials for different methods among each other. So starting with Lagrange, we have 5 points. So what's the degree of the polynomial to construct here? Of course, it's n minus 1, so it's 4, degree of polynomial 4. So you will remember the Lagrange interpolation polynomial form, and here we have the y0, the y1, y2, y3, and y4 already given in the table, and we need to construct the Lagrangian polynomial of degree 0 and the Lagrangian of 1, L2, L3, and L4. So L node is using in the numerator, as you remember, all the x values except what? Except its ith x, right? So except x node, we will use x minus x1, x minus x2, x minus x3, x minus x4, and in the denominator we will use only x node and subtract all the other x values from it in the products successfully like this, and then we substitute the x naught through x4 values, keeping the x of course in the brackets, and then we multiply the brackets in the numerator and the denominator. Usually the denominator bracket is constructing this constant, and then the numerator brackets is constructed the polynomial. Applying the same with the Lagrangian polynomial 1, L sub 1. Now we are using x minus x node and x minus x2, skipping x minus x1, and therefore we're using it in the denominator, constructing the constant of x1 minus all the other x's. And the same with the L sub 2, L sub 3, and L sub 4. Finally, we substitute their values beside the corresponding y. So this is y naught multiplied by L sub 0 or L naught plus y1 multiplied by L sub 1 plus y2 multiplied by L sub 2, and so on up till y4 times L sub 4, and then we distribute this constant and combine the like terms to construct this polynomial. So this is the required polynomial at the end. Perfect. And then let's go to the Newton. The second requirement is to apply the Newton. Remember the Newton, which uses which table? This was the polynomial, yes, and we have to construct the divide difference table. Exactly. This was the divide difference table, constructing the x values in the first column, the corresponding y's, polynomial of degree 0, and then higher degree polynomial using 2 points, and here the polynomial uses 3 points, so it's f of x1 and x2 minus f of x naught x1 over x2 minus x naught, and so on. So this is the polynomial here, the divide difference table for this data. Here are the x values, their corresponding y's, and take care while you are subtracting and dividing the values. This is the third column using the 2 points successive. So here we use y1 and y0, x1 and x0. Here we use y2 minus 1 minus 0 over 0 minus negative half, which is 1 over half, then it's 2. And this 2 is the 2 minus 1, which is 1 over the half minus 0. So again, it's 2. And the negative 2 is 1 minus 2, which is negative 1 over 1 minus half, which is half, which gets us negative 2. And then we go higher with 2 minus 2, which is 0. So senseless, whatever the denominator is, which is 0 minus negative 1. So 0 over 1, it's 0. And here it's 2 minus 2, again 0, with the denominator half minus negative half. The negative 4 here is constructed from negative 2 minus 2, which is negative 4, over 1 minus 0, the last x, which I can't reach by the cursor, this one at the end, minus the 0, and this will construct the negative 4, and then going further with negative 4 minus 0 over 1 minus 0, skipping this half, will construct the negative 8 over 3, finally with this value, which is negative 8 over 3 minus 0, divided by 1 minus negative 1, which is 2. So we have negative 4 over 3. Now use the forward gathering for or combining for the coefficients to construct the polynomial. So substituting b0, b1, b2 through b4 with the coefficient factors. Again, we distribute and combine the like terms in order to get this polynomial of degree 4, which is exactly the same one which we reached using the Lagrange here, right? So they are exactly the same, and this proves the uniqueness of interpolating polynomials using our techniques. Let's do the same with part B. So we have different data sets. Again, they are 5 points. So we are interpolating polynomial of degree 4, and we go forward to construct the L node through L4. L node is x minus x1, x minus x2, skipping x node, of course, x minus x3 and x minus x4. In the denominator, we will use the x node and subtract every other x value from it except itself, of course. And then the denominator is constructing the constant, which is here 1 over 24, and the numerator factors are multiplied together, constructing this polynomial. And please be patient and be organized in doing this. There are a lot of steps, yes, but not so many steps, but we need to be patient, and we need to make it right, because it's of course worth it at the end. So L3 and L4, and then directly we substitute using the y values, the polynomials in their Lagrange polynomial position in the interpolating polynomial, and then we distribute the constants and combine like terms to construct this polynomial. We will do the same, but using Newton, the same 5 points and the polynomial of degree 4. Now this is the polynomial of Newton, and we need to substitute the coefficients. And we know, of course, the x node, the x1, they are directly given. So the coefficients are getting from where? From the divide difference table, right? So let's construct the table, having the x values at the first column, the y corresponding values in the second column, and then constructing the interpolation through the last one, which uses 1 over 6 minus negative 1 over 6 divided by 2 minus negative 2. And this is our breakpoint, the last value minus the first value. And then we substitute these constant coefficients in the forward construction, this side of the table, of the previous table. We take the B0, B1 through B4 and set the factors of x minus x0, and here x minus x0 times x minus x1, and so on up till the fourth term here, and then we distribute and combine up to reaching the same polynomial that we reached using the Lagrange, right? Thank you for your attention. Have a nice day. Goodbye.